Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at some of the common misconceptions related to Chapter 16, and that deals with acid-base equilibrium. First, some of the common errors, as always, watch your units and sig figs. We'll also take a look at ion concentration of a compound and what you have to watch out for there. Identifications of acids or bases, core ideas of this chapter. In particular, salt acidity, how you handle that. Understanding the differences between the three theories we look at, some things about acidity and structure, and then probably the biggest problem people run into with the math stuff from this chapter, because we've already done a bit of equilibrium math, that makes it a little bit easier, but the salt pH problem is often one that people struggle with. So as far as watching your units and sig figs, in particular, remember KQ has no unit, so you're not going to stick a unit with there. Second thing to watch out for, remember when you're going from KC to KP, R should have the same units as the pressure. And since we're typically using atmospheres in pretty much every single problem, that's your 0.0821 value for R. Weak bases. Remember, we need a KB, not a Ka. Watch out for that. That's a really common way to report is if we're looking at in particular with salt type situations, they'll often give you the Ka of the conjugate of the weak base we're looking at because that's a typical weak acid. So watch that. Do you need Ka or Kb in a problem? They'll often just give you Kas. Fourth thing, weak acids. Remember, Kas for a weak acid give you H3O plus, but for weak bases, remember on top in our equilibrium expression, we're going to have OH minus. Be very, very careful for that because a lot of times they're just asking you for pH, and you need to be aware of what X is going to be when you solve and neglect X. When you see molarity and volume, remember, you should be able to convert that to moles. That's something you should start to recognize. Whenever they tell us a molarity and volume, oh, I can figure out the number of moles. Also be careful when mixing solutions. Make sure you have the total volume because if you've got how many moles in a problem and you're mixing things together, um, don't forget to add the two volumes to get your total volume to get your real concentration in the beaker. And then finally, with sig figs, remember if you have two significant figures in your concentration, as a p-value, that would be two decimal places and vice versa. Those are some common unit issues to watch out for. Second thing, ion concentration of the formula of a compound. This is something that often trips people up, especially if you're given the name and not the formula like I've written them here. You have to be very aware of what it is you're getting. So if we have something like 0.15 molar NaOH, um, since this is a strong acid we're looking at, I'm sorry, a strong base we're looking at here, remember that means it 100% ionizes into its two ions. Na plus and OH minus. So 0.15 would be the concentration of the sodium ions, and 0.15 would be the concentration of the hydroxide ions. But in this strong base over here, which also disassociates 100%, when you split this into its ions, you're going to get 0.15 molar with respect to the calcium ions. But remember, when one of these formulas breaks apart, you double your hydroxide. So you would get 2 times 0.15 molar when we're dealing with our hydroxide ion concentration. So that's going to equal 0.30 molar. Be very, 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 very careful of that. In particular, our strong bases. Because with strong acids like sulfuric acid, that's our only strong acid that is diprotic, more than one hydrogen. Remember, it doesn't dissociate 100% except with the first hydrogen. So something like HCl, which is a typical monoprotic strong acid, yes, the concentration of the acid equals, for this strong acid, the concentration of the H plus ion. Now, one thing to watch out for. This is a acid with one of our halogens in it. Those are typically strong with one exception, that one right there. So be careful, be aware and watch out for something like HF because even though our acid concentration here is 0.15 molar, this does not disassociate 100%. So you cannot say the concentration of this acid because it's a weak acid. You can't say it equals the concentration of the F minus or the F plus, more importantly. That is not true in this particular case. Now, when it does disassociate, it would be true that these two concentrations would equal each other, but it would not be true that they equal the concentration of the weak acid. So be careful of your weak acids in doing this, and in particular, watch out for HF because that's one people often mistake for a strong acid. Um, Number three, is it an acid or a base? There's a variety of things related to this general idea. One thing, even if it's a base, you're often asked to find pH. So be aware, and this was hinted in a previous idea, be aware that if you're dealing with a base situation, you're going to get OH minus when you set up your equilibrium problem. And if they're asking you for pH, you have to address that. So yes, if you get your OH minus after you solve for X and you take the negative log of that, realize you're calculating POH and you need to exploit that relationship to handle that. Um, this relationship is also important in some situations. And then finally, remember that Ka times Kb also equals 1 times 10 to the negative 14th. All of these are things you may need to be able to manipulate back and forth between in different problems. Next thing related to is an acid or base. When you've got a formula, if it doesn't clearly say whether it's an acid or base, then you need to sometimes know how it's going to react when you throw it in water. Now, acids, really what you're looking for is ionizable hydrogen. So does the formula start with hydrogen? That's often a dead giveaway that you have ionizable hydrogen. Another one to watch out for is organic acid functional group, the carboxyl group. Watch out for that thing because this is an ionizable hydrogen on there. This is not hydroxide, so be aware of that. We're not looking at hydroxide here. Also, in our salt problems, cations that aren't conjugates from a strong base, those things will function as acids. And then finally, um, when you see a formula, particularly when you're looking at structural formulas, you may see an OH on there. Make sure it's not on a carboxyl group. Make sure it's not a metal hydroxide type situation because then obviously it's going to be an ionizable hydroxide, not an ionizable hydrogen. And make sure it's not an alcohol. So when we have a situation where it's not an alcohol and it's obviously not a metal hydroxide, it's probably got an ionizable hydrogen hydroxide or ionizable hydrogen there. One thing to watch out for would be something like H2SO4. This is such a common acid. We see it all the time. It's one of our common strong acids. Well, when you see its structural formula, so when you're drawing the Lewis dot structure, it's a little bit more confusing because what you're going to end up seeing is something like this. And somebody may look at that and say, oh, that's an alcohol, or oh, that's a hydroxide. This thing is going to be a base. No, our oxyacids are oxygen stuck to some central atom, and some of our oxygens, one or more, are going to have hydrogen stuck to them. That's not an alcohol. That's not a hydroxide. That's an ionizable hydrogen in the case of sulfuric acid and other oxyacids. Now on the base side, remember you're looking for often ionizable hydroxide. So if it's a metal hydroxide, dead giveaway, you've got a base. Also watch out for your proton acceptors, which when you put them in water, because often they're negatively charged or they have an unshared pair that's uh, on a polar substance that can attract a hydrogen from water. So water is really HOH. This is a way to look at it. If we've got an anion, it can be attracted to this, pull that off of water, and what we did was we produced OH minus in water. That's a base function. So anions that aren't a conjugate of a strong acid, and also amines are an organic functional group um, or functional group that's often on organic molecules that can do this same thing. So watch out for those types of things. Next, salt acidity. Know your strongs. Remember, we got 7 strong acids we looked at and 8 strong bases. And remember, the 8 strong bases would be our group 1 and our heavy group 2, which would be the CBS substances we're looking at. So you need to know those 15 strongs because conjugates of them are negligible, and that's a very important idea in a number of situations in this chapter, including and in particular when we're looking at salt acidity. Now, our big 3 rules with salt acidity: conjugates of strong acids and bases are neutral. Cations form if it doesn't fit above. That's why this is rule 2 and 3 here. Cations form acidic solutions and anions form basic solutions. Remember, rule 1 trumps rule 2 and 3 with these. So if we throw a salt in water like lithium carbonate, first thing we need to do is evaluate our ions. Lithium, does that come from a strong? Well, since the cation, this would be coming from a strong base. So lithium hydroxide, is that a strong base? Yes, it is. because it's one of our group ones. So this is going to be negligible as far as acid-base behavior. So it's not an active ion. And that leaves us with carbonate, CO3 2 minus. Well, that's a negative ion. So is there a base? Yeah, well, there's carbonic acid, but it's not one of our strongs. So it's a weak. So this would be our active ion. CO3 2 minus is our active ion. Now, one of the things you need to be able to do with these is understand how it reacts with water in a typical acid-base reaction. So you should be able to write your hydrolysis for this particular anion. Well, what's it going to do? Remember, on our previous slide I had mentioned, it's often convenient to think of water as H plus OH minus. So as a negative ion, well, that can grab that hydrogen and we can end up making HCO3 minus. And what's left on the water? Well, what's left is OH minus, and that's how this functions as a base when we put it in water. So remember, you should be able to write the hydrolysis reaction for any acid or base. Next one, same idea, KBr. First we have to think about, does it come from any strongs? Well, KOH, yes, that is a strong. That's another group 1 strong like lithium. So that is negligible. And then finally, Br, HBr. That would be the acid it comes from. Yeah, that's one of our strong acids. Both of these are negligible. So this thing is going to have a pH of 7. Um, and we're not going to write a hydrolysis reaction for what it does in water because it doesn't make water produce any H plus or OH minus. So this one doesn't have a hydrolysis reaction that we're going to look at here. So, oh, and didn't mention on the previous one, but remember, because it made OH minus, remember when we throw it in water, that's going to make our pH greater than 7, just to note. Finally, the last one, zinc chloride, another ionic salt. Okay, the cation, that's zinc hydroxide. Well, zinc hydroxide is not one of our strongs, so that is going to be an active ion. Now we need to check our chloride. And chloride here, HCl, yes, that is one of our strong acids, so that's going to be negligible. And in this particular case, that means we have Zn2 plus as our active ion. Remember, we need to be able to write the hydrolysis reaction of that. So what's that going to do when we throw it in water? Well, as an anion, or I'm sorry, as a cation here, it's going to be attracted to our OH minus. Now we've got to balance this thing. So if it's a Zn2 plus, in this particular case, what we would do is we would look at it as grabbing 2 hydroxides. So, well, that means we needed to start with 2 waters here. And we need to basically strip 2 hydroxides away from 2 waters. So what we're going to be left with is 2 H pluses on the product side. So that would be our hydrolysis reaction that we get here. So this would be something that you need to be able to do. Now, if there was a fourth salt up here that was something like zinc carbonate, now we have an active cation and an active anion. How would we handle that? Well, what we really need to do is compare the Ka of this thing with the Kb of that thing. And if Ka was better or higher than the Kb, then we know it's going to be functioning as an acid. And if the Kb was higher, we know it'd be functioning overall as a base. So if you have 2 active ions, you have to look a little deeper and look at Ka, Kb values. Don't typically see that on the test, just something I wanted to make you aware of. Next thing, know the differences between our 3 acid-base theories and understand that, Arrhenius was our earliest theory. It's a little bit more limited than Bronsted-Lowry. And Lewis is even more general than Bronsted-Lowry. We can talk about acid-base behavior with Lewis situations that we couldn't talk about with Bronsted-Lowry. So we're going from our most basic, most specific to our most general in this order here. You need to understand the differences between the two because something may act like a Lewis acid, but it really wouldn't, in the particular situation we're looking at, wouldn't maybe be described as an Arrhenius acid because maybe it's not producing H plus in the situation we're looking at, or it's not producing OH minus in the situation we're looking at. And notice with Lewis, I didn't give you the actual definitions of these things as they're typically given. Really with Lewis acids, don't confuse it with Bronsted-Lowry. Don't think acceptor donor type stuff. Just be aware of 2 things. If it's a Lewis base, have pair will share. Remember the rhyme. So if we have something like water that's coming in and interacting with something, and it's interacting at our oxygen, so that's the active site where it's bonding, well, it's bringing an electron pair, so that's going to be our Lewis base. And Lewis acids are things that don't have unshared pairs. So at the site of reaction, they don't have an unshared pair there. So things like a proton H plus, metal cations, and also when you have double bonds at the active site, that double bond will break, and the other substance coming in is then bringing the um, pair. So it's going to have the pair will share, but the double bond site, that wasn't where it's at. So that would make that the Lewis acid. So watch out for those particular things. And in particular with Lewis, remember, draw the Lewis structure. Then you can see who's got the electron pair. Next idea, acidity and structure. Um, this is something that students often struggle with, so I want to try and reduce it to its most basic level and realize this is not a high incidence question, but there are 4 situations you need to be prepared for, and only 4. So really, this is at its minimum level what you got to watch out for. First, our binary acids. Those are 2-element acids, one of the elements being hydrogen. So we can look at some periodic trends with our binary acids, our group versus our period. Now, one of the things that we talked about in notes, and it's talked about in the book, is that there's some factors that can affect the strength of acids. Bond strength can play a role. Bond polarity can be a role. That's where Limpec and so forth can come into play that we've talked about before. Um, and it can be a combination of these, but in particular, when you're dealing with a group, what happens is bond strength wins, and the hydrogen stuck to the X, if it's too strong, it's hard to ionize that hydrogen. So you end up with weaker bonds as you go down a group. So that means you're going to get a more ionizable hydrogen situation. So within a group, typically what we're looking at is bond strength. And what happens there is as you go down, bond strength is going to be less. So your acid strength is going to increase as you go down. Now, in a period, bond strength is relatively even. So it's going to be a non-factor here. And really what becomes important is your bond polarity. And that's going to deal with your electronegativity and polarizability. As the electronegativity, as you increase it across a group, that's going to make the HX bond more polar and therefore more ionizable, and acid strength is going to increase. So when you go down a group, acid strength is going to increase because of weaker bond strength. And as you go across a period, acid strength is going to increase because of a more polarizable situation in your bond. Now, that actually is also something that's affected when we're looking at oxyacids. That whole bond polarity type situation is very important in our oxyacids. So first, you've got 2 different situations with binary acids, and then we've got oxyacids. Now, remember, an oxyacid is an acid in which an OH group, and this is not ionizable hydroxide. It's an OH with an ionizable hydrogen. So be careful, we're not talking about hydroxides here. So no metal hydroxides. And possibly other oxygens stuck to the central atom as well. So in the case of our simple substances here on the left and in the blue, we have HOBr and HOCl. So within these 2 substances, I know it looks like they're alcohols. I know it looks like it's a potential metal hydroxide, but it's not. It's a non-metal situation here, and that is not hydroxide because it's not an ionizable OH. That doesn't stick together. It's an ionizable hydrogen. This hydrogen can break apart in HBr here. It's ionizable. Well, in which case does it break apart more? Well, it's going to be the one with the higher electronegativity, just like we were looking at up here. So between these 2, if you look at electronegative trends on the periodic table, when you go down, electronegativity decreases. So um, in that particular case, HOCl is going to be our stronger. So high electronegative center is going to be more acidic. Now, the second situation here is where we have like a family of similar oxyacids. So our center atom is basically the same. So here on the left in the blue, we had same number of OHs inside that non-metal formula. Here we have the same central atom. So we've got 3 different, and they've got the same OH number in each case. Um, but what's really very different between them is the number of O's. Now, the more oxygens you have, the more polarizable this situation is, and the more it's going to free up that hydrogen to come off. So this would be our weakest, or number them in order of greatest to weakest. So in the 3 we're looking at here, this would be our greatest acid, and on down. So the more oxygens we have, the more ionizable that hydrogen becomes. So these are really your 4 situations to be aware of, and that's it. So Is it a binary acid? You got two things you're looking at. Is an oxyacid? You've got two potential situations here. Um, do you have the same center or a different center with the same number of OHs on it? So both of these are really same OH situation. So this is really a different center atom type situation. Okay, last thing is the one math idea that I wanted to look at because this is, if you're going to have trouble, this is the one where it typically happens because there's several different things going on here. So what is the pH of 0.043 molar potassium sorbate? They give you the formula of potassium sorbate and they go on to give you the Ka. Now, one thing you got to be aware of here is that Ka can be misleading because it may not be useful in its current form in the problem, especially when you're dealing with salt solutions where the active ion is the anion, because that's going to be a base reaction, and they're often going to give us Kas in these problems, so you got to be careful and be aware of that. But it also gives us a clue as to what most likely are um, active ion is going to be, although you really should do your evaluation. So let's start with that. First thing we should look at is what is our active ion? Well, K comes from KOH. That's a group 1. That's strong. So that's going to be meaningless. And then our sorbate here, well, if we stick a hydrogen to that, we're going to get our acid. Well, that doesn't look at all like any of our 7 strongs. So this is our active ion. And if that's our active ion, the very first thing we should do is we should write our hydrolysis reaction. So what we're going to have is C5H7COOH, and that's going to be reacting with water in a weak situation. And this negative anion is going to grab a hydrogen from the water, so we're going to end up forming C5H7COOH, should recognize our carboxyl group there, and OH minus. So this is definitely a base reaction. Now notice they give us the Ka of our conjugate here, and we really need to know when we set up our equilibrium expression, we're going to get a Kb situation. We really need to know the Kb of this thing. So when we go to write our Kq expression, in this case it's going to be a Kb, that's going to equal the concentration of C5H7COOH times the concentration of OH minus all over the concentration of C5H7, which is our sorbate anion. That's what this is going to look like. Well, that's a Kb, and they gave us a Ka. But don't fear, remember, Ka times Kb equals 1 times 10 to the negative 14th. So we can divide 1 times 10 to the negative 14th by our Ka, which is 1.7 times 10 to the negative 5th. And we would be solving then for Kb. So you got to recognize what's the active ion. You've got to recognize, oh, it's going to be a base reaction. You got to recognize that means we're going to be solving for Kb. So in this problem, I really need to solve for the Kb. Well, when you do the math between these two, what you're going to end up with is 5.88 times 10 to the negative 10th is going to be our Kb value. And the reason that's important is that's what we're going to plug in our previous expression here. And we're going to end up with an x squared, because these two concentrations on top will equal each other, over the concentration of our sorbate. So I'm just going to call that sorb minus x, and that's going to equal our K value, which remember was 5.88 times 10 to the negative 10th. Now, like all of our equilibrium problems in this chapter, first thing we're going to do here to make this an easier problem so we don't end up having to use the quadratic is we're going to do neglect x. And remember, when you do this on the AP test, yes, you should have that because that's going to be worth a point. And yes, you should write this neglect x thing so you show them you know what you're doing here. And what we're going to end up with is x, which is going to equal our OH minus concentration, is going to equal the square root of our sorbate concentration, which was given as 0.043 minus, I'm sorry, times our Kb value, which was 5.88 times 10 to the negative 10th. Now, when I plug that in and solve for x, and remember x is going to equal the OH minus, which is going to equal our sorbic acid, x ends up equaling here 5.03 times 10 to the negative sixth. Now, at this point, and this is something you need to do every single time you calculate an x, you need to check your percent ionization. So if you divide this thing by our original concentration, which was 0.043, and multiply by 100, so times by 100, does this equal less than 5%? Because remember, if this was more than 5% ionization or dissociation, neglect X is not valid. And you'd have to use either the quadratic or successive approximations at this point. But in this particular case, you're going to get a very small number. So we're well below the 5% mark. So to finish, we now have our confirmation that neglect X was valid, so that means this is a valid OH minus concentration. And here's where you got to be careful. This is OH, so if you take the negative log of our X, we are not getting pH. What we're getting is POH. So we would take the negative log of our OH minus, and then we would subtract that from 14 to get our pH, which in the end ends up being 8.70. So watch out for it's a base reaction. Check. Caught that. Did they give me the right K value? No. Check. I caught and fixed that in the problem right here. Next, neglect X. Did that. Next, was that valid? Yes, it was. When I did that math, it was less than 5%. And then finally, I caught that I had to subtract my negative log from 14 because it was a base reaction, not an acid reaction. And those are some of the common misconceptions related to these ideas to be careful of to make sure you don't fall for some of those problems. Now, like I've done the last couple of movies, I want to take a quick look at, in this chapter, some of the math and concept questions and where to look to get help if you need more help with them. And don't forget, remember, we use H plus and H3O plus interchangeably throughout this chapter. Um, H3O plus is what I typically like to use because I think it's a little better representation, but even that is really an oversimplification of how it really exists in real life. But typically I'll use H3O plus. Now, some math and concept stuff, don't forget, you should just be able to calculate pH from a variety of different sources. You need to know the relationship between all of these so you can go from one to the other. You also should be able to, and this is something we looked at in notes, to do some estimations with your pH and H plus less H3O plus concentration. So if they tell me the pH is 6, I know that that's 1 times 10 to the negative 6 as a H plus concentration. I can easily do that in my head. And as an OH minus, that would be 1 times 10 to the negative 8th. That's something you should be able to do. So if I know that it's 6.2, I know that this is going to go down a little bit and that's going to go up a little bit. So you need to be able to estimate values um, for pHs from concentrations and vice versa with some simple numbers. Also, don't forget the whole rounding and sig fig idea that we talked about earlier in the test help movie. Strong acids and strong bases, you have to know them and be able to write their dissociation. Typically, we write it as a hydrolysis, but sometimes you'll ask for the ionization. The difference between these is if we're adding water or if we're just breaking it apart. And remember, strong, single arrow, weak, double arrow for that idea. And given the concentration of an acid or a base, if it's strong, you should be able to calculate the H plus, the OH minus, the pH, and the POH. And there's a couple of sample problems in the chapter, number 8 and number 9, that deal with that. Weak acid math, and this is where equilibrium math comes in. Be able to write the dissociation either as a hydrolysis or ionization. Typically, we like to go there, but you should be able to do both. You should be able to determine the Ka from the weak acid concentration and the pH, because remember, if we know the pH, we know the H3O plus. which is going to be equal to our anion, and those two multiplied over the weak acid concentration minus whatever our OH minus was, because remember I'm sorry, not OH minus, our H plus here, we're talking about an acid. And we can then calculate the Ka from that. So be able to do that. Sample question number 10 from the chapter does that. Number 11 deals with another idea that you should be able to understand, which would be determining the Ka when you're given the percent dissociation, or another way of writing that, percent ionization. We use those two interchangeably. And sample problem 16.11 deals with that. You should be able to determine the pH, percent dissociated, or equilibrium from the concentration of the weak acid and the Ka. Problems 12 and 13 deal with that. Remember, you should be able to determine the Ka from the Kb of the conjugate. You should be able to understand the relative strength based upon Ka. Remember, the bigger the Ka value, the stronger the acid is, and that would be the weaker its conjugate base is. As far as weak bases, it's pretty much all of that stuff, but in the base perspective. So pretty much everything we just looked at in the last problem, but really from a base perspective. And it really starts by being able to write the ionization slash hydrolysis. And typically, remember, once again, we're typically looking at the hydrolysis reaction for this. And there are some sample problems that deal with some of the different things here. But this is really the exact same thing we talked about with weak acids, but from a weak base point of view. So in the last bullet point there, the bigger the Kb, the stronger the weak base is, and therefore the weaker its conjugate acid would be. Salts. Looked at a sample salt problem, but there's some other things you really should be able to do, pretty much all of which I talked about in the previous movie. And these are some sample problems that deal with those ideas, or in the case of this one, it's really the sample we did in our notes dealing with the salt problem, and as well as what I gave you in the test out movie. Identifying acids and bases using a variety of different theories. And remember, with Bronsted-Lowry, you should be able to write also their conjugates on the far side and be able to identify them. Um, Determining acid strength from structure of the two acids. Covered that very thoroughly in the test help earlier movie. Know if an organic molecule will be acidic or basic. Remember, carboxyl group is acidic. Amine, the NH2 group, that is a clue that it's going to be a base. Know when you use your quadratic formula or successive approximations, whichever one you prefer. And that's something you need to check for every single question on the test. I will say that they're not all going to be this way, but one would be fair game. And I will include the quadratic equation on the test for you. But you always need to identify, is the percent dissociation or ionization greater than 5%? Then you can't neglect X, and you have to go to quadratic or successive. Be able and know how to check for that and do it every single time. You should know the relationship between the successive ionizations of a polyprotic acid. And you should know that this is always going to be greater than that, which will be greater than that, and typically significantly greater. So the highest K will be the first ionization. And know how the strength of an acid is related to the strength of its conjugate. And that's it. Those are the key things that you need to be aware of to do your absolute best on the Chapter 16 test. Good luck.